Good morning, everyone. You're all doing okay, and are staying healthy, and continuing to make choices to keep staying healthy. Hope we're having a busy Tuesday thus far. We're back to at least a normal for this semester sort of week. So, a couple of announcements. We have, this is, again, normal for fall of 2020 weeks so far. So we'll have, unless otherwise stated, we'll resume having in-person lecture meetings and in-person labs for those who are able to attend. If you are not able to attend for any reason, there are optional online assignments and the lectures are being recorded for your benefit. So if you as an individual have a very particular strong reason to not be here, by all means, you don't have to come in. But if you are here, welcome. Glad to see you guys again. We will have a capture for an in-person lab this week. We have very stylish styrofoam cups and thermometers scattered throughout the room. Yes, our lab this week is going to involve thermodynamics and heat transference. Speaking of, this week we're going to be beginning chapter 8. This is the last of the new material before our next test assignment. This week is about thermodynamics, and then we're going to spend at least most of next week reviewing, going over everything that will be on the test together. So everyone's clear on what material will be present, going over some examples, and making another set of practice questions again. And the test will work similarly to last time, where it will be made available to you from the second half of next week into the start of the week after. And you can take it at any point that you find best at the time to be able to sit down and put time to do it quietly. It'll work again the same way. And after that test, we will begin getting into sort of exam season. This is the second of our 2 normal tests. Anything we cover after the test will just be added on to the exam. Additional announcement. Next Tuesday is voting day. And normally on Tuesdays we have, I have 2 lectures with the 2 different sections of this class, and there's a lab. In the spirit of making sure everyone, A, has time to study for the test, that is that week, and B, has time to vote. Everyone has a different situation depending on how far you are from your home address. There will be no labs next week for that period as listed, and we may have remote lecture Tuesday specifically. It's a review. That would be a review week anyway. So if you sign into what would be the class session, it would be for review purposes. If you feel you are reviewing on your own and don't need to attend, that is fine. But to give everyone as much time as they need to A, study, and B, vote, we will not be meeting in person next Tuesday specifically. Okay? And no lab next week at all. Any questions about any of these announcements so far? I will also send out an email with all the scheduling announcements because not everyone attends the lectures, and I need to make sure everyone gets it in written format. So that will be summarized in your inbox shortly. Okay. Tonight, the Chapter 7 assignments are presently due. I do need to make one quick apology because I have this document found up. The lab activity, that's not So the lab for Chapter 7, the one that is due today, if you have not completed it yet, got a lot of pieces. Let's see if I can find my saved file faster. Yeah, I can, look at that. So, this is the lab that is, that shouldn't say chapter 8. No, it does. So that's one more change needed to make to the document. Sorry about that. This is the lab activity, the remote lab from last week that is due tonight. If you have not already turned it in. The link to the States of Matter simulator was wrong. It was not the right link. Many of you noticed this, many of you emailed this, and as evidence of the fact it's not the right simulator, this is the picture of what the simulator should have looked like, and if it didn't look like this, you were in the wrong place. The link has been revised, and the document on the Brightspace page has been revised. The simulator is still available on the same website. You just have to find it at a different menu, but that is the new correct link. You have not finished the lab yet. In addition to that, the Chapter 7 homework and quiz are due tonight. So before we start anything else, I'll give you guys a chance to ask any Chapter 7 assignment related questions that you have before we move into Chapter 8 today. Yes?
Sorry, I'm just pulling it up. Okay, questions 5 and 6 on the homework.
Can you be more specific about what questions you have?
For question 6, just would you be using the specific heat formula? Or like what formula would you be using for number 6?
Okay, so this is homework chapter 7, question number 6. A person eats an amount of energy. This is how your body gets energy. It is stored in the food that you consume. You know the mass of the human and the height of the human and an estimated surface area of the human. We're considering the entire body to be completely water, which is not completely accurate, but it's close enough. If 80% of the calories we consume are converted to heat, and if you have no way of venting that heat, what is the temperature increase just from the food you consume? So this is a specific heat question. You know the amount of energy added into a system. You know the mass of that system, the being that the energy is being added to. You know what that being is made of. We're assuming that the human body is 100% water for this question for the sake of simplicity. So the specific heat that you want to use is that of water, which is in the tables listed in your notes, but this one comes up a lot, so feel free to write down that that constant is 4,186 joules per kilogram times degrees Celsius. And the last part of the formula is delta T. So you're solving for delta T. The problem is only asking for the change in temperature of Susan. I know the numbers change for different students, but does the name of the person involved change for anybody?
Yeah, it's always Susan.
Okay. So you want delta T for Susan. So this, as it is what you're solving for. You want to get delta T equals. You know the mass, you know the specific heat of water, and you know how much energy was added to her body. That said, you are told that energy in the form of kilocalories, so you do need to convert that to joules. There is a conversion that needs to happen first to get kilocalories into joules. I consider conversions to be sort of known constants. You are more than fine just looking them up on an electronic source, but I don't think I actually told you that conversion in the notes, and for that I apologize. That was an oversight on my part. There's certain things that I feel confident saying off the top of my head, and then there's certain things that I always want to double check because I feel like I'm very Okay, very good. So, 1 kilocalorie is equal to 4,184 joules. So if you needed the conversion, there it is. And for those unaware, this unit kilocalorie is the same unit as the calories written on your food packaging. Food packaging is actually written in kilocalories, although they indicate that by writing the calories with a capital C instead of bothering to say kilocalories. If it's calories with a capital C, it means kilocalories. So when you eat a pudding cup that says 100 calories, it's actually 100 kilocalories, and it just tells you how much energy is in the food. So, solve for delta T. You convert kilocalories to joules, plug that in for Q, mass, and C, and solve for delta T. From there, determine whether or not you think you would notice this temperature change. Keep in mind the unit that you get for this temperature change will be in Celsius, so don't base it on your knowledge of Fahrenheit. And then, this is admittedly a little bit more of a biology question, although it involves the methods of releasing thermal energy, transferring thermal energy, as we talked about before. Select the processes that really any human body can use to prevent your own temperature from rising. We have several built-in mechanisms to keep ourselves from overheating, which is good because we are warm-blooded organisms and our bodies create heat from food, unlike reptiles. So, go through this, select all of the methods that a body uses in order to get heat out of itself. And just to give a little bit of a hint, the reason that sweating works to cool us down isn't the sweating itself. Just releasing salt water from your body does not cool you down. What cools you down is the sweat evaporating off of you, because the water has to absorb thermal energy out of your body in order to evaporate. So if you've ever finished a really tough activity and you just wonder after the fact, why do I have to be so uncomfortable right now? Why do I have to sweat? It does cool us down, just not in a very fun way. As for the other question we were asked about, question 5, calculate the temperature increase in a known mass of water that results from the conversion of 13% GPE. Okay, so I can see why there might be a potential issue here. So we are looking at thermal energy being added to an amount of water. And we care about energy being added to a mass of water, again, specific heat of water is right here, in order to change its temperature. So we're going to use the same formula here. But this particular question also mentions GPE. If you recall, the formula for GPE is mgh. This represents the energy stored in objects' ability to fall. And any type of energy can be converted to thermal energy. All processes convert some energy into thermal. This water, its energy is going to be released out of the gravitational potential state. Eventually, an amount of it, the question tells us what percentage of this energy will become thermal energy. So, my numbers say 13%. Yours is 13%. Your percentage will be different. So I'm just going to write 0 percentage in here. You plug in your percentage value. But whatever percentage of that GPE is going to turn into thermal energy, you have to indicate as such. So 13% times the GPE formula, this is the energy that will become thermal energy. This is that 13%. And that becomes thermal energy, which is also equal to mc delta T. So this is sort of a transformation. It's a before and after state. Some amount of energy was GBE, now it's going to become thermal energy, which is going to heat up this mass of water. So we're going through a series of steps here. Our end goal is to get delta T. Now we know we want delta T, we know the specific heat of water, we know how high the waterfall is, we know the percentage of energy that became thermal energy, but we don't know what that total energy level was. We don't know what Q is, we don't know the mass of the water either. But can anyone see that we don't need the mass of the water? Okay, first thing we're going to do is I'm just going to cut out this middle step. These are all equal to one another. I'm just going to get rid of the Q in the middle. Does anyone have any issues getting conceptually to this step? Any questions at all? Feel free to write this down. Again, plug in your own numbers at home. Now it's the same water on both sides. If you throw a kilogram of water off of this waterfall, its own GBE is going to become thermal energy in that same kilogram of water. Which means the mass is the same on both sides. And there's just an M freely sitting in the equation on both sides, meaning if we divided both sides by M, it would cancel. So you don't need to know the mass of the water because every gram of water that goes over the waterfall is going to fall that height and have its energy converted from the thermal. So ultimately, your real starting point for your algebra is your percentage times G times H equal to specific heat of water times temperature change. And again, you want delta T. You want delta T equals blank. Any other questions, including issues still at 5 and 6? Any questions you have, please let me know, even if you have to ask in a difficult lecture. And you can send me any questions you have as you are working tonight, any at all at any time, about any of the assignments. If you guys are okay for right now, then what we're going to do next is we're going to begin looking at the Chapter 8 notes. This is a direct continuation, so we're not switching gears. This is thermal energy again. So some of this stuff will actually be useful in doing your Chapter 7 homework. So Chapter 8 is about thermodynamics. This is a word you might have heard before. We're just going to examine what it by itself means really quickly. Thermo is the prefix we use to describe anything involving temperature and thermal energy. Thermo, thermal, same root word. Dynamics, before we looked at physical dynamics, wherein objects are moving. Thermodynamics is where thermal energy is moving and switching objects and examining the science of what thermal energy is and how it interacts with the world around us as it transfers between things. So, in order to study thermodynamics, we have to look at the laws of thermodynamics. There are technically 4 of them. They're just not numbered 1 through 4. The 3 laws of thermodynamics were invented first, and by themselves they describe most every single thermodynamic process you could ever need. After these 3 were invented, we added the 0th law of thermodynamics. So 0th is like first, second, third, but it's a 0 instead of normal number. It's called zeroth because it's sort of the prologue to the other laws of thermodynamics. It's just an introductory statement to help your understanding of everything else. It's the opening. It's like the opening statement of the novel before you read chapter 1. So these 4 laws of thermodynamics help us to understand really all energy in the world around us, namely how it transfers and interacts with the thermal energy state. And we're going to spend time with all of them. After this slide, we will look at each one individually, but since they're all here, and since you're all copying anyway, let's at least describe them with cursory detail. Beginning with the 0th law of thermodynamics as the prologue to the other ones. If objects A and B are each in thermal equilibrium with object C, then objects A and B must be in thermal equilibrium with each other. Recall from before, thermal equilibrium is just a fancy way of saying they're at the same temperature. So, if, let's say our objects, object A will be the basketball, object B will be the dodgeball, object C will be me. So, I'm holding all of these objects. If the ball is at 25 degrees Celsius and it is in thermal equilibrium with me, we must both be at 25 degrees Celsius. If me and the softball, dodgeball, what's the name for these things? Like, what? That actually makes a lot of sense, so thank you very much. If the foam ball and I are at the same temperature, if the foam ball is at 25 degrees, and I'm at thermal equilibrium with the foam ball, I must also be at 25 degrees Celsius. And since both of them are in thermal equilibrium with me, they must also be in thermal equilibrium with each other, and we're all at 25 degrees Celsius. This is just the commutative property of temperature, basically. If you remember the commutative property for math, if A equals B and B equals C, then A must equal C. That's all this is. It's nothing new. It's just that principle as applied to temperature as a preface to the other laws. Moving on to the actual meat and potatoes laws, main course. The first law of thermodynamics is one of the ones that's most quoted, because this is the law that we call the law of conservation of energy. We've made mention of that principle before. The idea that energy cannot be created nor destroyed. You cannot make it and you cannot destroy it. There is a certain total amount of energy in the universe that is constant. It is only converting between forms and converting what object possesses it. If you looked at the entire universe as a system, you could say, billions of years ago, you could have said, there is exactly 1 quintillijoule of energy in the universe. And that would still be the case today. The entire time, we've just been playing switch backsies with what has the energy and what state it's in. The second law of thermodynamics is more commonly referred to as the law of entropy, which we will talk about more in detail later, but the elevator pitch for what entropy is refers to chaos and disorder. The disorder level of the entire universe does not decrease. It can only ever stay the same, or it can rise. And the third law, the entropy level of the entire universe might be rising, but you can decrease the entropy of a certain object. You can make a specific object more orderly. And you do that by reducing its temperature. When we talked about temperatures and what happens as an object gets colder and eventually approaches absolute zero, the coldest temperature that can exist, when an object has thermal energy, its particles are moving all over the place, jumbling, dancing, running into each other. The more thermal energy you have, the more the particles are bouncing off of each other. The less energy you have, the less they're bouncing off of each other. The colder something is, the more organized it is on a molecular level. Eventually, if you take every single ounce of thermal energy out of something and it is at absolute zero, it will be as organized as possible. Its particles won't move at all. They'll be locked into a nice, perfectly organized pattern. And that is the state wherein a single object can have the lowest possible entropy, which translates to the highest possible order. You can do that for a single object, just not for the entire universe. So these two laws are not in conflict with one another. You're just looking at different things for each one. So these are the laws themselves. Again, you have access to this slide. These notes are on the right space page. You don't have to copy them verbatim, but if that's how you learn, then please, by all means. We're going to begin moving through these one at a time and looking at some of the math related to each of them, one at a time. Before we do, though, any questions from anyone about anything? As you're pondering that, I need a quick water break. Anything else in there? Okay. So, moving on. We're going to define a few other terms really quickly. When I say the word system, I'm referring to some part of the universe that we are going to study. A system can be as large as encompassing the entire universe. You could say the universe is a system, and we're going to look at all of it at once. You can also say that a system is as small as a single subatomic particle. When we talk about a system, we're simply defining what we are looking at. And the surroundings of that system is everything else besides that system. If our system was 2 protons in an object, the surroundings would be every other atom in that object. If our system is 2 objects sitting on this table, the surroundings would be the table and the air around it and everything else in this room. If we were looking at the universe as a system, the whole universe, it really doesn't have any surroundings that we know of or understand. But when you are doing a problem and you're looking at a specific example, it is important to define the system you are looking at and separating it from everything else. Okay. Now the zeroth law, again, it is that this is just a specific example. The green text is just a specific example of the zeroth law. This is the commutative property of temperatures. If A equals B and B equals C, then A equals C. That's it. Now, I suppose you could call this a formula, but the first real formula of this chapter we're going to talk about here with the first law of thermodynamics. Now, the full definition of the first law of thermodynamics is energy cannot be created or destroyed. That means what we're going to take from that and translate into this specific formula, that there's a certain constant amount of energy within a system, and you have to factor that into any problem you are doing. If the system is a specific object, you're going to be looking at all of the energy that that object possesses, and all of the energy entering the object and leaving the object. So, the increase to the when I say internal energy, this refers to all energy types stored within an object, which is mostly just going to be thermal energy. So an increase in the thermal energy level of a system is equal to the amount of heat added to the system plus the amount of work done on the system. There's multiple ways to add energy into a system. You can heat that system up and it will have more thermal energy. If you do work on the system, if something outside of the system is doing work upon it, that will also add energy to it. Let's say, for example, that the system we're looking at is this chair. And I do work on the chair by exerting a force and moving the distance. In doing so, I added energy to the chair in the form of kinetic energy. So when you do work on something, you are giving it more energy. When you do work, positive work upon something, you are adding energy to it. However, it is possible for an object to do work on something outside of itself. If your system was, let's say, a piston, so, for those who have not heard the term before, a piston is basically a device built to extend. Usually what happens is there's a fluid inside of the piston that is heated and cooled, and upon expanding or contracting, some other part of the system moves in and out. You may have seen something like this physically on old-timey trains. There's usually a caster at the bottom and some rod extends in and out in order to make the wheels spin. There's a similar thing in cars, just pistons in the engine that go in and out to transfer energy from the engine into the wheels, etc. And in this particular object, if you do work on the piston, you are adding energy into it. And usually you do that by physically compressing the piston, forcing energy into its system. But if the piston uses up that energy and does work on something else, usually by extending and exerting a force, it is doing work on something. When anything does work on something else, it's losing energy. When I do work on something, I use up energy and give it to something else. Objects can do this too. If a machine does work, it is using up energy and sending it somewhere else. Work can be done on this machine. I can give energy to it, but it can also do work and energy can be taken away from it. Make sense so far? Okay. Now this formula here, I realize I don't actually explain up here what delta U is. Delta U refers to the change in the internal energy of whatever your system is. This is energy. This is basically the total energy that an object possesses. And that total energy changes based on what is happening to the object. So, I'll be right back. So, this doohickey is basically a piston. It's what contained in here is an amount of air, which is a fluid. That amount of air can exert a force on the plunger here to push it. If the air is exerting a force outwards, it'll push the plunger out. But if something else comes in and presses down on the plunger, you are doing work on the system and adding energy into this amount of air. So this is a piston that we were just talking about, and there's already a certain amount of energy inside of here. If I do work on the system by striking the piston, that energy level will increase. Eventually, it will press outwards, and some of that energy will be released from it. So right now, whatever its total energy level is, it's not, right now, I'm not touching it, right now its total energy level isn't changing in this moment. That means delta U would be 0. If I was to say, do 100 joules of work on the object, and its internal energy level stayed the same, if this was still 0, then the object would gain 100 joules worth of thermal energy. When you do work on something, if its internal energy level doesn't change, it will gain that energy as thermal energy. And as an example, hope I can make this work today. So, for those wondering what the heck I'm doing, I'm digging around for some pocket lint. And I'm going to open this piston. It does pop open. And I'm going to add this pocket lint, a small amount of it, and put it into the cylinder. And then close it back up. So, there is now lint trapped within this system. This system presently has no energy being added into it or removed from it. It's sitting by itself. Delta U is 0. Heat being added to it is 0, work being added to it is 0. What I'm going to do in a second is I'm going to strike the plunger, and in doing so I'm going to do work on the system. I'm going to add energy to it. And hope this works, because this particular machine is really fiddly as to whether or not the thing I'm hoping happens. I'm turning the lights off to make it more visible if it happens. So when I do work on the system, it's going to gain energy. And if its internal energy level doesn't change, it's going to gain that energy as thermal energy. And when something has thermal energy, occasionally it tends to can you repeat that word, actually? What'd you say? Rise. Well, you're not wrong. Rise in temperature, very good, and spark. What's supposed to happen is a little spark of fire that's supposed to appear in here, but it's very picky as to when it happens. It's really cool when it works, but it's not when it doesn't. Okay, I'm going to turn the lights back on, because even if you can't see the spark, there is still some evidence that thermal energy is being added into the system. I'm going to have to rely on those closest to the front to tell this to the audience, but those who are close up here, the spark isn't working today, but focus on what's happening in the tube after I strike it. So, those in the front, can you explain what you just saw? Thank you. And if you want to see this up close for yourself, you can, but even if there's no spark, there is still smoke. As I add energy into the system, it will take the form of thermal energy. And while it's not making it ignite, it is making it smoke. Which is a terrible habit. I need to get it to stop. Sorry, bad joke. So, there it is. Again, to define every single part of the equation on the previous slide, Q in general represents heat being added into a system. Q is going to be a positive number if thermal energy is being added to something. W is work. It is positive if work is being done by a system. That's where this can get a little bit confusing. You will plug a positive number into this formula for either Q or W if the object is gaining thermal energy or doing work. If the system does work, you plug in a positive W. If work is being done upon the system, you would plug in a negative W. So what I was just doing, as I add energy into the system, as I do work by exerting a force on the plunger as it moves, I was doing work on the plunger. That means I would plug in a negative value for W here, because I did work on the plunger did not do work. That make sense? Does that not make sense? Yeah. And then U is the internal energy level of an object, and a lot of the times U is going to remain constant, because the total energy level of an object might not always change if the energy in equals the energy out. But as a general rule, if internal energy of an object goes up, its temperature will rise. If something gains a total amount of internal energy, which includes its thermal energy, its temperature goes up. And which is why, one reason why, this system began smoking. As I added energy into it, it was not giving the energy out. As I gave it energy, the energy would remain in the tube. That drove the temperature of the contents of the tube up, which created the smoke. So, if U is 0, there's no energy in or out net at all. If U is positive, temperature goes up. If U is negative, temperature rises. We're going to end by looking at a couple examples of this. So will probably be the last thing we do today. Just a couple quick ones, because it's not a very complicated formula. Let's say that we are going to be looking at this particular piston. Really, either piston, physical one, the one drawn on the board, are fine to look at. The way that you would make this sort of a machine do work for you is there's some fluid inside of the piston, and you are going to heat it up. So in this first case, you add 600 joules of thermal energy into the air tank of a pneumatic piston. You're making it warmer. And what happens to things when they, in general, if you have a single object and you make it warmer, what happens to the particles of that object? The velocity of the particles increases, they bounce off of each other more, and the particles space further apart. So when you heat something up, it gets bigger. You don't notice this very much with solids, but all objects are bigger when they're at higher temperatures. This is most obvious with air and other gases, because as you heat up the gas inside of this tank, it's going to expand. And as it expands, it's going to press the plunger of the piston outwards. And that's how you get work done out of the machine. Again, if you look at the wheels on a train, the piston extends, that makes the wheels turn, and then as it pulls back in, it pulls the wheels back, and this process just continues repeatedly. if you've seen or ever looked at the casters on an old steam train. All objects expand when they're warm, even solids, which means the Empire State Building is taller on the hottest day of summer. Cast your mind back to whenever you've been traveling and you've gone over a bridge. If you ever recall a bridge that probably has like these weird metal bands every couple hundred yards or so, okay, not hundreds of yards, but every couple yards or so, these weird metal bands that look like they're sort of teeth interlocking, and you usually feel a da-dunk, 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 da-dunk as you're going. Those are there because objects expand when warm. If you were to build a bridge that was just a single long slab of concrete, that's going to heat up in the summer and expand. And if it gets longer, it's going to press into the ground, and that's just going to create a weird force that will ultimately either blow it upwards or crack it. So those weird little gaps, the metal gaps with the teeth, are natural spacers, so that each individual piece of concrete has a little room to grow, and you don't grow too much into the earth around you and make everything fall apart. So those are there because of thermal expansion. Solids expand a tiny bit, gases expand a lot, which is why we put gas inside these things. So, for problem 1 specifically, I'm going to erase the homework questions we looked at. Delta U equals Q in minus work out. We are going to add 600 joules of thermal energy into this system. So, it's going to be 600 right there for Q. The piston is then going to extend and do 400 joules of work. So, as the gas inside the tank got warmer, it's going to expand. As it expands, it presses the end of the piston outwards so that the gas has more room inside. And in doing so, it's going to do 400 joules of work. There's already a negative here. If you do work, if the system does work outside of itself, then you plug in a positive number, which means the negative stays intact. And so, the total energy, the internal energy level of the system is going to go up by 200 joules. In this act, we gave it 600 joules, and it used 400 of them to do work. That means it kept 200 of them. You put in 600, you get 400. You put this much energy into a system, and it does this much work. That remaining 200 isn't gone, it's just stuck inside of the machine in a state that we can't use it in. All machines are like this. You put in some amount of energy, it'll do an amount of work less than that amount of energy because some of the energy is stuck inside the machine as internal thermal energy making it hotter. Every machine does this. No machine humans have built will ever perfectly, you give it a certain amount of energy and it'll do the same amount of work. No human-made machine can do that. Always in real life, some amount of thermal energy will remain inside of the object. This has to do with the efficiency of the system. Meanwhile, a second machine pushes into the system and does 1,000 joules of work into it. If the total energy of the piston does not change, how much thermal energy does the piston gain? So, delta U equals Q minus W. If the total energy level isn't changing, U stays at 0. Q minus the work done on the system. A second machine pushes into the piston and does 100 joules worth of work into it. The system is not, the piston we have been examining is not doing work now. Work is being done on it. Since work is being done on the system, we have to plug in a negative number. Does that follow so far? Okay. What that ultimately means is 0 equals Q plus 1,000, which means Q needs to be equal to negative 1,000. If you do work on something and it stays at the same temperature, delta U is 0, delta U is 0, the temperature of the object remains the same. If you do work on something and the temperature remains the same, that means any energy it gains has to leave it somehow. So this object is releasing thermal energy outwards from itself. In doing this, it is venting its thermal energy out of the tank, or making the surroundings warmer. You would see this in a machine like a refrigerator, because the coils on the back of it are constantly releasing heat after you pressurize them and force heat out of the fridge so that it's not in the refrigerator. I've been rambling a lot today, so we will continue talking about these topics in more detail. And if you have any questions you want to comment or continue to work into Chapter 7 assignments. Any questions you have, I'm glad to see you all back, but please remain cautious, stay healthy, make good choices, and you all have a wonderful day. Sorry.
Huh? Huh? Two? That's the one you do. I still in two. Huh?
Right. That's because every single task you perform, if you use up 1,000 joules of energy doing something, and if your goal is to give all 1,000 joules of energy to whatever task you're working on, odds are maybe at best 999 joules will actually make it into the object. Because every single process, some energy is going to get lost to friction in some part of the system and become thermal. Every process is inefficient in that way. Like with the piston over there, you put in 600 joules, but it only did 400 joules worth of work. So all processes lose that little bit. I don't know why I snapped at that.
So on question 1 of the quiz, I was typing in the correct answer because I had answered wrong the previous 2 times, so I didn't delete. Okay, this is going to sound really contrived, but you know how sometimes with sapling, you'll press check answer without realizing it, and it'll submit, and it'll be wrong. I did that for question 1, and I was just wondering if I could get an extension, like one more extension, because I have the correct answer, like I wrote it out.
It'll help me remember if an email is sent.
Yeah. Okay.
Can you show me the answer and the work in the email, and then I'll just go in and give you
Yeah, okay, I'll do that.
Okay.
Thank you.
You're welcome. Let me just switch the camera off real quick.